Okay, piecewise functions are functions that are created literally how it sounds like, just with multiple pieces. And those multiple pieces can be any shape. They could be parabolas, they could be square root curves, but we're exclusively in our linear applications unit, so all of our piecewise equations are going to consist of lines. And so what we've got is we've got one graph that shows Anne's distance in miles as a function of time in hours. And it's one function, it's her trip. It's not like each piece of this is a separate function. It's just that she's traveling at 4 different rates, and she travels different distances during those periods of time. So not every piece of this equation is going to look exactly the same. So the way that we write this equation, if you look at question 1a, it says write a function for this equation. And so all we're going to do is we're going to, let me go to the next slide because I have some empty space. We're going to name our function, d of t, it's distance as a function of time. We put our equal sign like we were going to write a regular equation. But what we do is we start this very large set bracket. And in that set bracket, we're going to list all of the various pieces of our equation. So what I'm going to do is I'm just going to write each of these linear pieces. So this first section of the graph right here is a line. It's got a y-intercept right here, which makes it very easy to write the equation for it. And it's got a slope of 3. So it's a really easy line to write. It's just 3t. And don't write it as 3x because we're doing time in hours. They've already told us d of t is our function notation and our variable. Okay? Then the next thing we do to differentiate, because if I just left this as a 3t, that line would have to keep on going in this direction and this direction forever, which it did not do. This line only existed from time 0 right here to time 1 right there. That was it. And this was 1 hour. Okay, so what I'm going to do is I'm going to write a domain restriction after that tells me that this function only exists between time 0 and time 1. Okay, so that piece is done. So then the next piece of the equation, so the second piece, let me go ahead and switch colors so we can differentiate. The second piece is this piece of the graph. And the slope of it is easy to calculate. We can very easily do our rise and run triangle or use these 2 points at the ends to determine our slope. The trick is that you can't just write the equation with just the slope. I mean, yes, we know the slope is 2/3 because we rise 2 as we run 3. But you can't just write it as 2/3 t because that would be the line with a slope of 2/3 and a y-intercept of 0. And we don't know where this line would have had a y-intercept because the y-intercept doesn't exist on the graph. So what I want you guys to get in the habit of doing is stop thinking everything has to be simplified into slope-intercept form. People tend to be really obsessed with slope-intercept form, but we really like point-slope form. We being pre-cal teachers, calculus teachers, we really like that form. So we do a lot of writing our linear equations like this. And in fact, all of first semester calculus is nothing more than slopes of lines, and they're going to use this equation an enormous amount. So what I'm going to do is I'm just going to change it up. I'm going to write this equation right here in point-slope form. So I already know, let me switch colors again so I can make it stand out. I already know my slope is 2/3. I know that x has been changed to a t, okay, and then I'm going to choose a point on that line. So let's say I just chose this first point right here. So that's the point 1, 3, and so I would put my first x coordinate in there and my first y coordinate in there. Now the only other thing I would need to do, because at that point my equation is this, y minus 3 equals 2/3 t minus 1. The only other thing I would need to do is I want you guys to notice that this right here, d of t, remember it's function notation, it's a fancy name for y. And so that means that your equation has to be in y equals format. And so all we have to do is we have to take this minus 3 and add it to move it to the other side. Okay, so what our equation would then become, okay, sorry, the doorbell rings, so I've kind of forgotten where I was, but this equation would just be, I've got my 2/3 written down, I would insert parentheses here and put the minus 1, and then of course the plus 3 had to move over there to be with it. And then this section of the graph exists between time 1 and time 4. So I'm going to put a comma, I'm going to put a 1. Now I have two options here. I can put just strictly less than t, because at time equals 1, I've already attached it to the first piece of the equation. But at time equals 1, these two sections of the graph are in the same place. And because of that, I can go ahead and just put less than or equal to. That's not always an option. Okay, but that goes through time 4. Then the third piece, of course, is just this horizontal line section. Of course, writing the equation of a horizontal line is super easy, and it exists at y equals 5, or in this case d of t equals 5. So I'm just going to write y equals 5. There's my third piece. And that piece of the equation exists between time 4 and time 7. So I'm going to put 4. Remember, you can do strictly less than, because the less than or equal to is already accounted for here. Or you can go ahead, because once again they do meet here at that same point, and put less than or equal to, and it goes all the way up through time 7. And then using the same strategy for the final piece, this final piece up here, as I did for this piece right here, I'm going to use my point slope form, because there's no way to discern what the y-intercept would have been. On some graphs, like this section right here, you could have just, taken a ruler and extended the line and you would have seen where the y-intercept is. This one you don't have that ability, because it would be way off the bottom edge of the graph, if that makes sense. So you're really going to want to stick with your point slope form for that one. And that section has a slope of 5/3. You're running 3 when you're rising 5. And then you can use any point on that graph. You could use this one, you could use this one. I tend to just stick with the first point on that section. So my slope is 5/3. And if I use this first point right here, it's at time 7, so t minus 7, and then plus 5. And that section of the graph exists between time 7 and time 10. So there's how you would write the piecewise equation. And writing it like this is telling the person who's reading it that all 4 of these, they're related to each other somehow. They are simply different sections of the same path, of the same function. If you wrote them as separate equations, you're telling someone who's reading it that they have no relationship with each other. They all represent different things. Okay, so that's why we do piecewise equations. So then the next thing on B says find d of 3. And so remember, this is still just your function notation. Remember that this little t right here was just replaced with a 3. So they're saying figure out what y is when x is 3, is essentially what they're saying. Okay, and so here's where time is 3. You figure out what section of the graph you're on. You're on this section right here. Now sometimes you would have gotten lucky. You would have taken this x value and you would have had a nice clear y value where you hit a grid line. That's not the case here. So what they're trying to make you figure out is, how am I going to calculate y? And the way you're going to do it is you're going to take this x and you're going to plug it into the equation. But because this equation has 4 different pieces, you have to figure out which piece to use. So if I backtrack just a quick second, when time is 3, that puts me on the second piece of the graph, which means I'm going to be in the second piece of the equation. And so time equals 3 falls into this interval right here, in between 1 and 4, and that's telling me to take that x value, that t value, and plug it into this equation right there. And so that's what we're going to do. We're going to do the 2/3 t minus 1, that is parentheses by the way, plus 3. And that's the piece of the equation. We're going to take this t value and plug it into the equation. And so we would have 2/3, plug in the 3, and 3 minus 1 of course is 2. And so we have 4/3 plus, and you can do plus 3. I'm going to go ahead and rewrite it as 9/3. And I really like improper fractions. That's entirely up to you, but I would say 13/3 is the y value. If you want to convert it to a mixed number, that's perfectly fine. Of course, that would be 4 and 1/3. And you want to confirm that graphically it matches. And so sure enough, it looks like it's at 4 and 1/3. And so d of 3 is 4 and 1/3 or 13/3. Okay. Now, the real reason that I wanted to make this video is because of the final two parts. It sounds like it's something completely foreign, but it's actually really easy because we've already done most of the legwork for this problem. So C says, draw a graph of Anne's speed in miles per hour. So I want you to remember, speed, of course, is just a rate of change. Well, all 4 of these sections are lines, and lines have a constant rate of change. And of course, the word we use for the rate of change of a line is slope. And so what they're asking you to do is draw a graph that shows the slope in terms of time and hours. And so what I've got here is a blank grid paper. And so I need to draw my axis. I'm going to go ahead and draw. Here's this axis. There's this axis. This is still going to be time in hours. And of course this is 1, 2, 3, 4, 5 on down, 8, 6, 7, 8, 9, 10. But this time this axis is going to be Anne's speed, and it's going to be in miles per hour. Okay, well, speed, as I've already said, is the slope or the rate of change of her graph. The first section of the graph had a slope of 3. And that section of the graph existed from time 0 to time 1. So what that means I'm going to go ahead and scale this. You can scale it however you want to. I'm going to go ahead and scale it in 1/3. So here's 1/3, 2/3, this would be 3/3, which would be a speed of 1. 4/3, 5/3, 6/3, so a speed of 2. And this would be my speed of 3 up here. And so from time 0 to time 1, she has a speed of 3 miles per hour. So I draw a horizontal line. Let me change colors so that you can tell it's not just a little hash mark right here. Okay. Then at time 1, her speed changes. Her speed becomes 2/3. And so over the course of the next time interval, from time 1 to time 4, she's on a section of the graph with a slope of 2/3. So from here to there, there's a horizontal line because her speed is constant. It's a constant 2/3 slope over the entire time interval from 1 to 4. Now, before we can graph those last couple of sections, I want to tell you what it is you're going to have to do at the breaking points. At time 1, right here, she changes speed. Now, at time 1, she's going to have a speed. We just don't know which of those two speeds it is that she's still currently traveling at, because theoretically, if you imagine, she's driving a car or something, as soon as you hit the brakes, your speed changes almost instantaneously. And so there's literally a jump in the graph or a break in the graph. And so what you need to do is you need to figure out where you think at time 1, which speed was she going? Was she still going 3 and she hadn't hit her brakes yet? And so what you would do then is you would put a solid dot right here, and you're saying that at time 1 she's still traveling 3 miles per hour. But then what you would have to do is you put an open circle or a hole there, because you're saying at time 1 she's not traveling at 2/3 miles per hour yet. She is literally in the process of transitioning down or decelerating. Okay, almost instantaneously again, if that makes sense. So then at time 4, same thing. You can decide what is it that she's going to do. I'm going to go ahead and say that she's still traveling 2/3 because then the next period of time from 4 until 7, she's not moving. Her slope is 0. She's on a horizontal line section. And so from time 4 to time 7, she's not moving at all. She took a rest, stopped somewhere for something. Okay, and then from time 7 to time 10, she's traveling at 5/3 miles per hour. And so I'm going to come up here. There's 3/3, 4, 5/3 would be right here. Oh, and here's 10. Right there. And so this is what the graph of her speed would look like. It would be a bunch of horizontal line sections with breaks in between. At those breaks, you get to choose which section gets the solid dot and which section gets the open circle. And then the final part is to write the piecewise equation for that. And that's going to be even easier. It's still going to have 4 pieces, but it's going to be speed as a function of time. It's still going to have the same time intervals. I mean, it still goes from time 0 to 1, time 1 to 4, time 4 to 7. But we're just going to write 4 horizontal line equations. So the first linear equation, of course, was 3. And that existed from time 0 to time 1. Now, I'm going to let me choose a different color here. I know it's getting kind of cluttered. I can go to the next page or blank slide if I need to. I went ahead and I put less than or equal to because I had put the solid dot here. So at time 1, I said that we were on that horizontal line section. When I jump down to the line section that has an equation of 2/3, I can no longer put less than or equal to because I have an open circle here. Because these 2 pieces, this piece right here and this piece, are not in the same location at time 1, I don't have the option of using the equal sign for both of them. So I'm just going to do strictly less than. And this one I went all the way up to time 4 with a solid dot. Like that. Okay. Then at time 4, I jump down to a horizontal line at 0. So my third piece would be 0. It starts just past time 4. So strictly less than again. I have that open circle. So I can't put less than or equal to. And it goes all the way up through time 7. And then the last one is, of course, the one at 5/3. And so they're all 4 just horizontal linear equations. So that's why we wanted to walk you through it. We wanted to make sure that you knew how to turn a distance versus time graph into speed versus time, but also how to write piecewise equations. And so now your goal is to work through the remainder of this activity on your own over the weekend. And of course you can get help when you get back to class on Monday, or you can message me if you have questions or something like that. Have a good weekend.